Welcome to The Explainer. Today, we're going to take a guided tour of a modern command and control framework called Black Obsidian. We're going to break down exactly how these sophisticated tools operate from the inside out. So how do these modern cyber attacks really work? Behind the scenes. We always hear about the initial breach, but what happens right after that? How does an attacker actually stay in control? Well, it almost always comes down to a really sophisticated piece of software that acts as a remote headquarters for the entire operation. And this is what's known as a command and control framework, or just C2 for short. You can think of it as the central nervous system of an attack. It lets an operator send commands and get data back from machines they've taken over, all from one central dashboard. Okay, let's dive into the details. Here's how we're going to break down Black Obsidian. We'll start with the server. Then we'll look at the implant it controls, then the secret channel they use to talk, cover its most advanced features, and finally, we'll see the whole thing in action. First up, let's look at the very heart of the operation, the server. This thing is the attacker's mission control. It's the command center where all the decisions get made. So the server is written in the Go programming language, and that's a pretty telling choice. Go is fast, it's efficient, and it compiles down to a single file, which makes it incredibly easy to deploy pretty much anywhere. This server is built to be a robust, organized hub for managing all the compromised machines, which it just calls clients. Now, check out how the server's database is structured. This isn't just some messy collection of log files. No, it's a really well-organized system. You've got distinct tables for keeping track of the agents, for queuing up commands, storing the results, and even managing files. This level of organization is absolutely crucial for pulling off a complex attack. And this right here, this one line of code perfectly illustrates a key evasion technique. See, this is where the server sets up its communication endpoint. But look at the path. /please subscribe /v1/users. It's designed to look like a completely normal, totally innocent web path. Why? To avoid raising any red flags with network security tools that are out there hunting for malicious traffic. It's clever. Okay, so we've seen the server. Now let's shift our focus to the other end of the connection, the implant. You can think of this as the secret agent, operating out in the field on the compromised machine. Its entire job is to be lightweight, super sneaky, and really efficient. It's written in C, which gives it great performance and low-level access to the operating system. It's basically the server's hands and eyes on the target system, carrying out orders silently in the background. The implant pretty much runs in a simple, continuous loop. It periodically calls home to the C2 server to check for new tasks. If there are any, it executes them. Then it gathers up some basic system info and sends the results of its work back to the server. It's just a constant cycle of getting orders and reporting back. And to blend in even more, the implant doesn't just make random web requests. It uses a list of really common user agent strings, just like the one you see here for a standard Chrome browser on Windows. This makes its network traffic look exactly like a regular user browsing the web. It's just another clever layer of evasion. So how do the server and the implant actually talk to each other without being overheard by, security software or network analysts? They can't just send commands in plain text, right? They use this awesome multi-layered communication protocol. First, a command is encrypted with AES 256, which is a really strong encryption standard. Then, that encrypted data is encoded into base 64 to make it look like harmless text. And finally, that whole package is sent over a standard HTTPS connection. It's kind of like putting a secret message in a locked box, putting that box in another locked box, and then sending it with a secure courier. This is the function on the server side that handles all the encryption. It takes the regular command, scrambles it, and gets it all ready for transmission. It's the first step in locking down the communication. And then on the implant side, you have this function that just reverses the whole process. It takes the encoded data it gets from the server, decrypts it, and reveals the original command that it needs to execute. All right, now for what I think is the most sophisticated part of this framework, its ability to run brand new tools on the fly without ever writing a new file to the hard drive. This is an absolute game changer for stealth. This is all done using something called a beacon object file, or just BOF for short. The best way to think about a BOF is like a specialized gadget that you'd send to a secret agent for a very specific mission. It's not a full program, just a small self-contained tool designed to do one thing really well. So why is this so powerful? Well, first off, it's completely fileless. Nothing ever gets written to the hard drive, which leaves zero evidence for forensic teams. Second, it pretty much just waltzes past most traditional antivirus software because they're focused on scanning files. And finally, it gives the implant dynamic capabilities, letting the attacker deploy new tools whenever they need to. Now, this is the technical magic that makes it all possible. The implant actually has a custom-built in-memory ELF loader. This component can take the raw BOF code, map it into memory, link it up, and execute it, all without ever needing to rely on the operating system's own loader. And this function right here, run ELF, is at the very core of it all. This is the engine that drives the whole BOF capability. It's responsible for carefully mapping the raw file data, sorting out all the details, and safely executing these tools right inside memory. Okay, so we've covered the server, the implant, their secret communication channel, and the advanced BOFs. Now let's put all the pieces together and walk through the entire life cycle from start to finish. So here it is, the complete life cycle of a single command. It all starts with the operator. The implant checks in using that disguised URL we talked about. The server sends back the encrypted command. The implant decrypts it, sees that it's a BOF command, so it downloads the payload and uses run LEF to execute it directly in memory. The result is then encrypted and sent back to the server, and it pops up on the operator's screen. It's just a clean, stealthy, and incredibly efficient cycle. You know, understanding these systems, from their database structure all the way to their fileless execution techniques, is really the first step for anyone in cybersecurity. But it leaves us with a critical question. As offensive tools keep advancing like this, relying on in-memory execution and encrypted channels, how on earth must our defensive strategies and tools evolve to keep up?